I know, full house. Class after this is like this basically every day, just like 1 or 2 people in the classroom. Everyone else is on Zoom or they just watch the recording. Yeah. Semester. All right, it's 5:30. Let's go to get started. All right, good evening, everyone. All 3 of you. How are you guys? And 7 people on Zoom. How are you guys doing today? Yeah. All the people who are watching this on YouTube later. Oh, hello, everybody. Okay, so today we're going to be starting something new. Well, not super new, but different from diffusion. We're going over how to do convection problems with finite volumes. Okay? So we're kind of just trudging right along. Like I said, following the same kind of path we did with finite differences. And so after diffusion comes convection. Okay. All right. So announcements, remember homework 5 is due this Friday, so in a couple of days. So make sure you are doing that. You should have everything that you need to complete homework 5 at this point. And then let me know, of course, if you have any problems with it or if you need any help, especially with the coding stuff, because the coding stuff is going to be a lot more relevant now. Once we get to the final project stuff.
Professor?
All right, I think that's all my announcements. Are there any questions I can answer before we get started for today?
Professor?
Okay, all right, so let's go ahead and get started. Oh, sorry about that. I think the audio is off. Yeah, sorry about that. The volume was down. Sorry, Alessandro. Go ahead and ask your question again.
About the homework, I was
Yep.
wondering, is it possible that the selected solutions are wrong?
It could be. I
Because
make mistakes on those sometimes.
because
Uh,
the way my answers came out, it kind of seemed like these were the solutions for the boundary conditions being in different locations.
okay. Go ahead and send me your work. I'll take a look at it tonight. And then if there are issues with my solutions, then I'll let you know.
Okay,
I'll let the whole class.
I'll
Yeah.
come by office hours tomorrow.
Okay, great. Yeah, that'd be perfect. Yep. Thanks, Alessandro. Yeah, sorry about that. I write all my homework solutions from scratch, and sometimes I do them in a hurry. So yeah, sometimes there could be mistakes. But yeah, if you find anything like that with the homework, always just let me know. And more often than not, it's usually my mistake. So yeah, just let me know. Okay. All right. So the topic for this for today and probably for Monday and next Wednesday as well is convection with finite volumes. Okay. Okay. And so, like I mentioned before, we're basically following the exact same path that we do with finite differences. So if you recall from earlier this semester, after we learned about diffusion, then convection was the next point of order. The only difference now is that we're doing with finite volumes instead of finite differences. Okay? Okay. And so just to remind you, we'll start with the 1D case today, and then we'll do the 2D case on Monday. Our convection formula looks like the following. So we have U partial phi partial x equal to A partial squared phi partial x squared plus Q. Okay. Although I guess because we're in 1D and we don't have any times, these can just be regular derivatives, but we use kind of partial and regular derivatives kind of interchangeably. Okay. Okay, and so of course, this term right here, this is our convection term. Okay. Its distinctive features are the fact that we have a convection velocity out in front and we have a first order derivative, right? So those are kind of the two main characteristics of our convection term. Okay. So just like we did with diffusion, the way that we're going to derive our finite volume equations is we're going to take this differential equation and integrate it over the cell. Okay. After we perform that integration, remember, we always simplify things by applying our integration trick. So whether that be divergence theorem or whether that be trapezoidal. All right. So today, what we're going to do is that we're going to go through that process. We're going to see what that integration looks like. We're going to see how that changes our finite volume equations relative to our diffusion case. We'll learn how to apply boundary conditions, and then we'll apply it all into an example. Okay, so that's kind of the plan for today. Are there any questions on this so far? Okay, so before we get to the kind of the math, let's just remind ourselves very quickly what convection is all about. Okay. All right, so relative to diffusion, right? So remember, diffusion is kind of this passive transport that just kind of happens just automatically, right? Convection is a lot more of a forced process. So convection is the forced Convection is the forced transport of a substance via a moving fluid. So whenever you have convection, you have some kind of convection velocity. And the idea with convection is that, whatever you're trying to transport, whether that be temperature, if you're looking at a purely heat transfer case, or if you're looking at mass transfer, this could be like, the concentration of a particle or something like that. Okay. It's going to move along with the fluid, and it's going to be transported from basically point A to point B along the fluid's path. Okay. Okay. So, visually, maybe we start out with some kind of blob of energy or blob of substance there. Okay. And it's just going to ride along with the fluid. Until it reaches a new location, just like that. Okay. And so because of this, whenever we have convection, things get transported along that velocity direction. Convection has this unique property where direction is very important. Okay? And so whichever way the velocity is going, that's where, that's something we need to take note of, right? In purely 1D case, this direction is either just going to be to the left or right, it's fairly simple. But then, in 2D, we have the multidimensional thing as well. Okay. And it was important, for one main reason, or the main reason that we talked about was stability. And so what we saw is that if we weren't careful with how we discretized our convection, so if we just kind of naively use the central difference scheme and we use a very large grid spacing so that the Peclet number might be very big, we could end up with unstable solutions. Okay. So the way we fixed this, there was kind of two fixes for this, if you recall. And so the first fix, which some people would argue is kind of the easier one, is just to refine our grid. Remember, we had this quantity called the Peclet number. And so the Peclet number was delta X times U divided by. Okay. Where delta X was our grid spacing, U was our velocity, and K is our diffusion coefficient. Okay. And what we saw was that in order to get a stable solution, this quantity here has to be less than 2, right? And that's if you wanted to use a central differencing scheme. And so if you're using a central differencing scheme, you would basically take delta X and you'd make it smaller and smaller by refining the grid until this Peclet number was less than 2. Okay, so that was kind of the easier way to do it. Dealt with it. It was a little bit more intrusive was something called upwinding. Okay? And so if you recall, this is when we use either a forward difference or a backward difference to discretize the convection derivative, and depending on which direction the convection velocity is going. Okay? Okay. So I want to remind you of these things, because once we start doing this with finite volumes, these ideas are going to come up again. They're not going to show up in the exact same form because finite volumes is different than finite differences, but they do, we are still going to have the same issues. It's just that the way that we deal with them is going to be different, or I should say the details of how we deal with them are different because of finite volumes. Okay, but I want you to kind of remember this because these properties here of convection, the directionality and the idea with the Peclet number, this is relevant no matter what method you're using to simulate convection. So whether you're using finite differences, finite volumes, or even finite elements as well. So these issues are always there, no matter what, because convection is convection, no matter what method you use to solve it. It's just that the way that you deal with them is just slightly different in each. Okay. Any questions on this? Okay. All right. So let's start with the 1D case, just like we always did. We'll see how this kind of breaks down, and then we'll move on to the 2D case in the next section. Okay, so we have 1D. Convection diffusion with finite volumes. Okay, so let's start with our equation, and I'm going to write it in a slightly different form just to make it a little bit easier to integrate. And so I'm going to say d dx of u b minus k d dx of dx is equal to q of x. Okay. That's the 1D form of our convection diffusion equation. So we have our convection term, we have our diffusion term, and our source term. Okay. And so just like we did with the diffusion last week, we're going to integrate this over a 1D cell. Let's say that we have a cell defined here, right? So I'll call the left side of the cell, we'll say the left side of the cell has a coordinate of x underscore L, and the right side of the cell has an x coordinate x underscore R. We're going to be integrating from the left side of the cell to the right. Okay, so let's go ahead and apply this to our equation. So we have integral x sub L to x sub R of d dx of u b dx minus integral from x sub L, x sub R, k d dx 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 is equal to integral from x sub L, x sub R, q of x, dx. Okay. Right. So all I did so far was just I took our original equation and just integrated it over the cell. So I just added all the integrals. Okay. And so fortunately for us, a lot of terms in this expression are going to cancel. So we have this dx is going to cancel with this dx. Okay. And so on the left-hand side, we have a lot of perfect integrals. And in fact, I'm just going to combine them into one. And so, if we do that, we have integral from x of L, x of R of d u b minus k d b dx is equal to integral x sub L, x sub R, cube x dx. Okay. And so those d terms there, they're going to perfectly cancel out with the integrals. iPad would behave. Okay. And so on the left-hand side, we have u phi minus k d phi dx evaluated from x sub L to x sub R is equal to integral from x sub L, x sub R, q of x dx. Okay. And so the left-hand side, all we have to do is just evaluate that quantity at the two ends of the cell, so x sub L and x sub R. And I'm going to do a step on the right-hand side at the same time. And so let's simplify this integral using the trapezoidal rule. Okay. Just so that we don't have to apply that integral. So remember the trapezoidal rule, the way that works is we're going to take our integrand here. So our integrand is just q of x, and we're going to evaluate it at x sub c, which is the centroid of the domain. Okay. Okay. And so on the left-hand side, we have the following. So we have u b minus k d dx evaluated x sub R minus quantity u phi minus k d dx at sub L is equal to q of x sub c, where x sub c, that this is the, remember, this is the physical location of the centroid of the cell. And we're going to multiply that by delta x, where delta x is the length of that domain. Okay, so it's the length of the cell. Okay. Okay. So let me pause here. I'm not going to box this just yet, but this is kind of a good time to pause just to because we're about to apply kind of a lot of stuff here. Are there any questions on this so far? Okay. All right. So the right-hand side's basically done. And so, we don't need to work on, we don't need to work on the source term anymore. So this is done. Okay. Right. The only thing we'd have to do at this point is, just plug in for a specific case, but, there's no more integration to do on that side. So I'm going to focus completely on the left-hand side. And in particular, I'm going to look at these two big quantities here. Okay. And so what's special about these two quantities, you can see that they're both quite similar. The only difference here is that they're being evaluated at different locations on the cell. Okay. But they are being evaluated at the edge of the cell. So let me draw a visual here just so that you can kind of see what's going on. Remember, we're still in the 1D case. Okay, so our cell in question is bound by these two x coordinates. So it's bound by x sub L on the left and x sub R on the right. Okay. In the middle here, in the middle of the cell, we have x sub c. So x sub c is the location of the cell centroid. And the solution value at x sub c, we give the symbol phi sub c. Right? So what I'm also going to draw in this image here are the two neighboring cells, right? So I'm going to draw the right neighbor and the left neighbor. And so the value of the solution at the right neighbor or the centroid of the right neighbor is phi sub r. And the value of the solution in our left neighboring cell is phi sub L, okay? But remember, we're focusing mostly on just this cell right here, which I've bracketed. But I've drawn in the neighbor values here just because we're going to make use of them in our equations. This phi sub r, that's our right cell neighbor. And this phi sub L is our left. So okay. And so with that in mind, let's go ahead and evaluate our face values or our edge values relative to the self-centered values. Okay. Okay. And so there are four face values that we need to do. Okay. I'll start with the familiar ones. Just because these were present in diffusion as well. Okay, so we have basically the solution derivatives that we're evaluating at the cell edges. Okay, so we have d phi dx at x sub L and then d phi dx at x sub R. Okay, and so d phi dx at x sub L. Remember, we use our forward difference here, so we evaluate this as b sub c minus b sub L divided by delta x. Okay. And then d phi dx at x sub r, this is going to be phi sub r, it's phi sub c divided by delta x. Right, so those are the same as diffusion. And in fact, they actually come from the exact same place. So if you look at the terms in our expression up here, that are the derivative values at the faces, these come from diffusion. Okay. And so if we come back up to our original equation right here, that takes care of this term and this term as well. Okay. I'm crossing them out, not because we're canceling them out, but just only because we have expressions. Okay. Next two quantities that we have to find out are the value of the solution itself. So phi itself at x sub r and x sub L. Let's go ahead and write those expressions out here. So phi at x sub L is equal to phi at x sub r is equal to. Okay. All right. So what do these mean? And so, when we say we want the value of phi at x sub L, we want to find the value of phi, or we want to have an expression for the value of phi right here. Okay. So with the pink arrow, I've drawn basically the location of where we want the phi value. The problem is, and that might seem trivial just because, phi is something that we're essentially solving for in our equations. The problem is that, we don't actually have phi at this location. We have phi at the cell centers, but not at the cell edge. So we do not. And so there's no value that we can just directly plug in here for that. Okay. But what we can say is that this x sub L is right in between, like literally right at the midpoint between phi sub C and phi sub L, right? And so one thing that we can do is to say that, if this location here is right in the middle of them, then its value, we can reasonably estimate it as the average of the neighboring cell-centered quantities, okay? And so the expression that we're going to use is the following. So I would have phi sub C plus phi sub L divided by 2. That's simply just the arithmetic average. And the same thing for the value of phi at x sub r. So we're also going to take an average here. So you have phi sub C plus phi sub big R, all divided by 2. Okay. Okay. So let's go ahead and take these expressions and plug them into our finite volume equation up here. Okay. All right, and so if we do that, we get U times phi sub R plus phi sub C divided by 2 minus K times the quantity phi sub R minus phi sub C divided by delta X, okay, minus U phi sub C plus phi sub L divided by 2 minus K phi sub C minus phi sub L divided by delta X. Equal to is equal to Q of XC times delta X. Okay. Okay, so now we're in business because now we've basically taken all of those cell center, or excuse me, all the face values, the values that were being evaluated at the edges of the cell, and we put them in terms of cell center values. Okay. So now let's simplify this. And so to simplify this, what I'm going to do is I'm going to sort things out in terms of coefficients, okay, for the various phi terms. And so I'm going to skip a lot of that just for the sake of time, but I'll go ahead and give you the result. And so the result for this is minus U divided by 2 minus K divided by delta X. This is multiplied by phi sub L plus 2K divided by delta X, phi sub C plus U divided by 2 minus K divided by delta X. So R equal to Q of XC delta X. Okay. And so what this equation is right here is that this is our algebraic finite volume equation for an interior cell. And this is the case when we have both convection and diffusion. So it looks a little bit different. If you really wanted to simplify this, you can probably do what we usually do. You can multiply this whole equation by delta x, and so that gives you a delta x squared on the other side. But you can also leave it in this form right here. And some people find this form a little bit easier to. Okay. So you can manipulate this equation however you want, and I see people do this sometimes, on the homeworks and on the exams and stuff like that. So that's totally fine. So if you want to multiply this entire equation by delta x, that's totally fine. Just make sure that you're consistent in terms of how you're applying those algebraic manipulations. Okay, any questions on how we obtain this result here? All right. And so because this equation here, it applies for all the interior cells, we can just apply this one straight up. And so as long as our cell has a left neighbor and a right neighbor, this cell will give us our algebraic equation. Okay. Of course, we have to modify what we do for the boundary conditions, but we'll cover that in a second. Okay, so the next step is to cover boundary conditions. Boundary conditions for convection, diffusion, FV. Okay. Let's go ahead and take a look. And so just like before, we're going to have two types of boundary conditions. We're going to have our Dirichlet boundary conditions and our Neumann boundary conditions. And so let's see how they're applied. Let's start with Dirichlet boundary conditions. Okay, and just like before, remember our case here is going to change depending on if we're on the left or right side of the domain. Okay. I'm going to do one on the left side of the domain first. Okay. And so let's say that we're focusing on this cell right here. Okay, so this is phi sub c. We have phi sub r right next door. Okay. So I guess this is an example. Okay. I want to emphasize that this is an example because if the Dirichlet boundary conditions on the right, you would have to kind of go through this process again. Okay. Okay. And so if we're on the left side of the domain, we can say that our Dirichlet boundary condition here is that phi is equal to phi naught. Okay. Dirichlet C on left side cell. And what we want to do is we want to find the finite volume equation for this cell. All right. So I'm going to go back to our form of the equation, or let's go back to our finite volume equation before we plugged in the edge values. Okay. So just like we did with diffusion. Let's start with u phi minus k d phi dx, evaluated at x sub r minus u phi minus k d phi dx, evaluated at x sub l is equal to cube xc delta x. Okay. All right, so we had both our convection and diffusion terms, both evaluated at one term for the right face, one term for the left face. I use the term face and edge, they mean the same thing. Face is a little bit more relevant in 2D. So edge is a little bit more relevant in 1D, but they mean basically the same thing. Okay. And all this is equal to the source term Q of xc times delta x. Okay. Okay. And so remember, the reason we start here is that we're going to modify one of these, and so we're going to do something a little bit different on the side that has the boundary condition. Okay. So let's look at the right side. The right side of the cell, we have a neighbor, right? Because the right side of the cell points towards the domain interior. And so since we have a neighbor on the right, we can just do our normal thing for this, for this term here. So phi sub r exists, our right neighbor exists, so we don't have to do anything special for that. But for the left side, we don't have a left neighbor, right? If we look for our left neighbor, we're just going to go over the edge of the domain. And so we're going to modify this. To account for the Dirichlet boundary condition. Okay, so let's go ahead and do that. And so on the right side, the ones evaluated x sub r, those are going to be the same. So let me go ahead and drop in the usual values for this. Okay. So that is exactly the same. So there's no need to change that at all. All right, and then on the left side, we're going to change these. And remember, we have two things we need to evaluate here. We have the value of phi itself. Okay, so we have the u times phi from convection. Okay. So let's start with that. And so we have this u times phi here, where this phi is the value of phi that's on the left edge of the cell. Okay. And so we're in luck. We have a Dirichlet boundary condition there. And so the thing with the Dirichlet boundary condition is that it tells you exactly what the value of phi is at that side. Okay. And so for this convection term right here, instead of u times phi, we're going to have u times phi naught, because that's exactly what the boundary condition is. Okay? And so that's kind of the nice thing about Dirichlet boundary conditions, at least in this case. Okay? And then for the diffusion term, we did this before. And so we're basically going to modify our forward difference to account for that edge value. Okay? And so this can be phi sub c minus phi naught divided by x delta x divided by 2. Okay. Because remember, we're only traveling half the distance because we're not traveling a full cell's distance. We're just going half a cell to the edge. Okay. And then our right-hand side stays the same here. So we have q of xc times delta x. Okay. Okay. Any questions on how we obtained this this equation here? All right, so let's go ahead and simplify this. And so just like we usually do, we're going to keep all the unknown phi terms on the left. All the known quantities we're gonna move to the right. And so this includes every term with phi naught, because phi naught is a given Dirichlet boundary condition. And so that's something that we know. Okay. And so if we do that, and so we move everything over to the right-hand side that is known, of course, we're going to clean up the left-hand side to make and group like terms. And so if we do that, we end up with the following equations. Have u divided by 2 plus 3k divided by delta x times phi sub c plus u divided by 2 minus k divided by delta x phi sub r is equal to q at xc delta x. And then here come our boundary condition terms. We have u e naught plus 2k e naught all divided by delta x. Okay. Okay, and so that's how you deal with a Dirichlet boundary condition. Okay. And so hopefully, you're starting to see a theme with finite volumes in general. So whenever you have a boundary condition, you're going to take our usual finite volume equation and you're going to modify it in order to account for that boundary condition. Okay. All right, any questions on this? Okay. All right, and so you should see here that it changes things quite a bit because now now without the left neighbor, now we have a convection contribution on phi sub c, which is we did not have this before, and the coefficient for the diffusion for phi sub c increased by 1. Okay, so in the default case, this was only 2k over delta x. Now we have 3k over delta x because of the Dirichlet boundary condition. Okay, so now let's do a Neumann condition. And let's do a case where we do it on the right-hand side of the domain. Okay, so let me draw it out visually so you can see what's going on. So our cell in question here is going to be here. Okay. So our phi sub c is right on the right edge of the domain. But we do have a left neighbor here, and our left neighbor is phi sub l. Okay. And this side of the cell right here is x sub l. Let me put this on top just to make it consistent. So l. Okay. And on the right side of the cell, because it's on the edge, we need to have a boundary condition here. So a boundary condition, it's a Neumann boundary condition. And so we're going to use the symbol gamma. Okay. But I'm going to change the terminology a little bit. Trust me, it's going to make our lives a lot easier. Because normally when I say we have a Neumann boundary condition, I say that it's the derivative that's equal to some value, right? So we say that d phi dx or d phi dn is equal to gamma. Okay. I'm going to redefine it a little bit and say that another way to interpret a Neumann boundary condition is to say that it represents the flux of a quantity. Okay. If you haven't seen this term flux before, I get confused between the different classes. I don't remember if we covered. Honestly, don't remember if we covered in this class before. Might still be hungover from Sunday. But when I say flux, what I basically mean is that this is going to be the basically the raw amount of transport that goes across that boundary. So that's kind of another kind of physical interpretation or physical way to interpret the Neumann boundary condition, is that it tells you how much of that quantity is going over the edge. Okay. Okay. So let's write out our finite volume equation, and we're going to start from the exact same spot. Okay. So we're going to start from our finite volume equation before we plugged in our edge values. And so that was U phi minus K x at x of R minus U phi K b phi dx at x of L is equal to Q of xc times delta x. Okay. And so just like before, we're going to take, the left, all the terms on the left face together, or the left edge, all the terms on the right edge together, and we're going to see which ones we can plug in our normal thing. So we're going to do something normal, or the ones that we have to kind of adjust for the boundary condition. Okay, so let's start with the terms that are defined on the left edge. And so since we have a neighbor on the left, and so since we have a neighbor on the left, we can do the normal stuff for this. And so we don't have to change anything about this. This one is good. I mean, we still have to plug in for it, but in essence, it's good. Okay. First, by process of elimination, and you probably already guessed this just by looking at the figure. Okay. The terms that are evaluated on the right edge of the cell, we need to adjust for the Neumann boundary condition. Okay? So this quantity here is going to be modified or changed to fit the boundary condition. Okay. Okay. And so before I do that, before we plug in any values, let's take a look at these terms. And so I group these terms together, since the beginning, very, for good reason. Okay? And so what this term here represents, this represents the overall amount of transport of the quantity phi across the right edge of the cell. And so whatever phi crosses the right edge of the cell, that's what this term represents. And by extension, the other term represents that as well. And so if you look at the term on the left side, the one that we said, we're all good to go, that represents this transport of phi across the left edge of the cell. Okay? And so I group these terms together, one term on the right, one term on the left, to represent the fact that, whenever we have finite volumes, a lot of times we're interested in the amount of transport or the amount of flux of phi across the cell. Okay. And transport can occur via one or two mechanisms. Okay? And so one way is convection and diffusion. And that's what our two terms there represent. So inside here we have U phi, okay? And so U times phi there, that's basically that represents the transport of phi via convection across the right edge. And then we have K d phi dx, And so that represents the transported phi via diffusion across the right edge. And so together, whatever phi is transported, we capture that mathematically in this term. Okay. So why am I bringing this up now? So why kind of bring this up kind of so late in the class? Well, if you go back to how we redefine our Neumann boundary condition, our Neumann boundary condition also represents, the total transport of phi across the cell boundary. Okay? In other words, the flux. And so what we can do is if we say that this amount here is the transport of phi across the boundary, what we can then do is that if we have a Neumann boundary condition, then the Neumann boundary condition is going to replace this entire term in the parentheses. And so it actually makes things very easy because, that entire term in the parentheses just becomes one number, okay? So mathematically it looks like this. And so we have the entire term there, we just have gamma, okay? So that is all good, okay? And we have minus u times phi sub c plus phi sub l divided by 2 minus k phi sub c minus phi sub l divided by delta x is equal to cube xc delta x. Okay. Okay. So just like before, let's go ahead and simplify this. And so all the known terms are going to move to the right. And so this gamma term here, since that's a given Neumann boundary condition, we can move it to the right-hand side. Okay. And so if we simplify, so simplifying this expression, what we get is minus u divided by 2 minus k delta x phi sub l plus u over 2 plus k over delta x sub c is equal to cube xc delta x minus okay, so this is an example of an equation that you would get if the Neumann condition was on the right. But again, I'm gonna give you one word of caution, why I still kind of have your attention. And so remember, this is for the case when the Neumann condition was on the right. If the Neumann condition was on the left, then you're going to end up with different signs on a lot of these terms. Okay. And so I want you to be careful about that. And so, I did these examples the way I did, kind of deliberately. And so when you're going to do the homework problems, and you're coming up with boundary condition equations for the cells, I want you to start, from these types of equations and kind of work out the math. Okay. And so don't just kind of plug into these equations right here, because first of all, you're not going to get the right phi values here. But second of all, the signs are going to be mixed up as well. So you want to be really careful with that with finite volumes. Okay. Any questions on this? Okay. All right. So I have one more example in the notes, but I think I'll save that. I'll save that for next time, just because we're definitely not going to be able to get to the code today. And so when we come back on Monday, we'll go over the hand calculation example as well as the code. But there is one more thing we can cover today in the last 15 minutes, and that's this idea of upwind. Okay. And so remember, when we were at the beginning of class today, we said that one thing you always have to keep in mind of whenever you're doing convection is this idea that your solution can go unstable. Doesn't matter if you're doing finite differences, finite volumes, finite elements, that risk is always there. So convection just kind of breeds instability. That's just kind of the way it is. All right, so one thing you can do to make sure that you're stable is you can check the Peckway number. Remember, the Peckway number is U delta X divided by K, okay? And so if your grid spacing is small enough such that the Peckway number is less than 2, okay, then you will have a stable solution. And so the good news for finite volumes that this is true for finite volumes as well. Okay. And so if the only thing that you get from this is that just decrease the grid spacing and you're all good. That's true for finite differences, finite volumes, and even finite elements as well. Okay? Okay. But just like we talked about with finite differences, sometimes that's not an option. So sometimes, maybe you have a situation where the velocity is so high that, you would have to have a very, very tiny grid spacing in order to get this to work. Or maybe you're working with a limited computational budget. And so you only have a certain amount of time, or the computer that you're using is a potato. And so you only have a certain amount of RAM that you can devote towards a solution. Okay. So sometimes, reducing the grid size is not an option. A very common example, more physical example, let's say that you're working with in the aerospace industry and you're working on simulating kind of hypersonic flows, right? And so you're looking at the flow of air or the transport of heat through an aircraft engine. Okay? And so in those situations, the fluid velocity is so high that it's just impractical to set the grid spacing small enough. Okay. And so you need to have other options. So there needs to be other options for you to get a stable solution when it's just not possible to get the Peckway number small enough. Okay. And so for those situations where you just cannot refine the grid for whatever reason, okay, you're going to have to use an upwinding scheme. And so that means actually changing the numerics or changing the approach to our problem. Okay. Okay. So I'm going to focus solely on the convection term. So I know that diffusion is there as well, but diffusion usually is not an issue. And so I'm not going to worry about that. Okay. So let's look at the convection case in 1D. Okay, so let me go ahead and draw. Let's draw a typical cell. So we have phi sub c, that is our normal cell. Okay. Cell-centered value. All right, on the left-hand side, we have x sub L. On the right-hand side, we have x sub R. Our right neighbor is given by phi sub R. And our left neighbor is given by phi sub L. Okay. Okay. And so during our finite volume process, during the process that we just went through in class today, remember part of that process involved estimating the value of phi at x sub L and x sub R. In other words, the cell edges. Okay. And so we had, during our finite element, or excuse me, the finite volume equation derivation, we had to estimate the value of phi at x sub L and x sub R. Okay. If you recall, all we did was to say that, since this x sub L here is right in between phi L and phi sub C. Okay. We just took a straight up average. Okay. So we said phi, the phi value at x sub L is just going to be phi L plus phi sub C divided by 2. And then same thing on the right. So on the right, this is going to be phi sub C plus phi sub R divided by 2. Okay. Right. So that seemed to make sense at the time, right? And so physically, this location here is right in between the two cell centers. And so the value of phi must be the average in between those of those two. Okay. And so this approach, this kind of averaging approach here, this is basically the same thing as a central difference. Okay. Because we're weighing the two cells, the two neighboring cells equally in performing this calculation. Okay. And so intuitively, that makes a lot of sense. Unfortunately for us, convection sometimes doesn't make a lot of sense. And so, let me go ahead and draw a convection velocity over this guy, just so that you can kind of see what I'm talking about. If I can get blue. Okay. And so let's say we have a convection velocity and it's going from left to right. Okay. So if our convection velocity is going from left to right, that means the upstream side right? Remember, the upstream side is basically wherever the velocity is coming from. The upstream side is on the left. And so if the upstream side is to the left, ideally that would mean that, in order for us to get a stable solution, a stable upwinding scheme, we should place more emphasis on the left-hand side, okay? Let's see what that looks like in our equation. And so in our equation, we had u times phi minus k dx at x sub r minus u times phi minus k dx x sub L is equal to q of xc delta x. So remember, the velocity is going from left to right. Okay. All right, so with that in mind, let's go ahead and plug in for these edge values here. Okay. And so let's start on the right-hand side. And so on the right edge of the cell, I should say. So I'm going to start with the diffusion term, because the diffusion term, no matter what's happening, that's still going to be the same. Okay. And so for the diffusion term, we're still going to plug in phi sub r minus phi sub c divided by delta x, all times k. Okay. And then for the convection term, normally we plug in the average, right? So we plug in phi sub c plus phi sub r divided by 2, right? But that's a central differencing scheme. What if instead we applied an upwinding scheme where we place more emphasis on the left, right? And so, and this is really hard to do on the iPad, with some people in here, some not. Okay? I'm gonna zoom in on this. So this is basically the situation that we have right here. Okay. As we have phi sub r, which is right in between phi sub c and phi sub r, or excuse me, x sub r, which is phi sub c. I'm getting confused. I'm so hungover. Okay, give me a break. All right. And so normally, we would do phi sub c plus phi sub r divided by 2. Okay. But if we wanted to place more emphasis on the left, because that's where the velocity is coming from, what if instead we just use phi sub c, right? Because that's the self-centered term that's on the upstream side. All right, so let's go ahead and see what that looks like. And so we come back to our equation here. Okay. And so instead of u times the average, let's just do u times phi sub c. Because this is the self-centered value on the upstream side. Okay, so let's do the same thing for the left edge terms. Okay, let's start with diffusion, because diffusion is going to be the same. Okay, so we have phi sub c minus phi sub L divided by delta x times k. Okay. And then for the convection term, once again, we're going to look at the situation at x sub L. I'll come back in a second if you're not done just writing it down. Okay. Okay. So now we're looking at x sub L, right? We want to place more emphasis on the upstream side, which is coming from the left, right? And so instead of taking the average between those two values, what if we just take phi sub L? Okay. Let's go ahead and apply that to our equation here. Okay. And so instead of u times the average, let's do u times phi sub L. Okay. So this is the cell on upstream side. All And of course, all this is equal to our source term here. Can't forget that. So it's q of xc times delta x. Okay. All right, so now our equation has changed quite a bit. And so we're going to get different coefficients because of our upwinding scheme. Same as we did for finite difference, right? So remember when we applied either forward or backward difference in finite differences, it changed the nature of our equation. So we're going to get the same thing here as well. Okay? So let's do the same thing. So let's go ahead and simplify this. And so if we simplify this and we group the like terms, we get minus u minus k over delta x b sub l plus u plus 2k by delta x b sub c plus minus k x sub r is equal to q at x sub c delta x. And so this is our finite volume equation. With upwinding on the left side. Any questions on this? Yeah.
The diffusion terms stay the same because they're not affected by the difference.
Exactly, right. Yeah. Yeah. It was like that with finite differences too. So finite difference, remember, we always use the same scheme for diffusion. So the same thing for finite volumes here. Okay, all right. And so, of course, this is, you're going to get different coefficients if your upwinding is going to be on the right side. So if you have a negative velocity that's going from right to left, that's going to place more emphasis on the right. And so, you're going to go through kind of the same exercise. Okay? And of course, because our typical finite volume equation with upwinding is changing our equation here, that's going to change a little bit how we apply our boundary conditions as well. Okay, but we'll go through all of that over next week, and we'll start doing 2D problems next week as well. Okay. Okay, so that's all I got planned for today, or that's all we have time for. So thank you guys for coming today. If you have any questions on the homework, especially if my coefficients seem wrong for problem 2 on the homework, I'll check it myself today too if I have time before I go home. And then please let me know. All right, question in the chat: do we have a second midterm? Yes, we do have a second midterm. It's not going to be next week. It's going to be the week after next. Yeah, so next week I'll put out a study guide for the next midterm. I'll record a review video as well. And so right now it's planned for the Monday, a week from Monday. So not the next Monday, but the Monday after that. Yeah. Yep. Mm-hmm. Okay. All right. So thank you guys for coming. I hope you guys enjoy the rest of your day. If you guys enjoy your weekend, and I will see you guys next week. Thanks, Anthony. Have a good day.
All right, Shane.
See you, Dominic. Have a good weekend.
I didn't see you in there. I was on the